Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So in this problem, we are given a couple of equations and asked to come up with a realistic problem for which these are the correct equations. Now, obviously, answers to this can vary, but the problem I came up with is a box is pushed along a surface, accelerated to a speed of 10 meters per second, and then the pushing is discontinued. The coefficient of friction equals 0.8, and the box has a mass of 1,500 kilograms. What acceleration will the box experience after the pushing stops? So the reason that I set it up like this is because it's pretty clear that one of these equations, the first one is for the x direction, one of them is a force balance for the y direction with a normal force and a gravitational force. So there's no other forces in the y direction here other than those two. And then if you look at that x force balance equation, it looks like there's only one force, and that force being a friction force, because you've got a number times the normal force. So that's why I've set it up like this. Just going to fix this because this should be 0.8. And we do need to have a free body diagram. So let's go ahead and create that. So as I said, there's only two forces in the y direction. We've got the normal force and the gravitational force. And then after the pushing has discontinued, we just have the friction force. So presumably the box is moving in this direction, and the friction force would be directed in the opposite direction. So now that we've got our free body diagram, let's go ahead and solve this. So let's take equation number 2 first, and we'll go ahead and solve for n. So we'll pull the 1,500 times 9.8 over to the other side, and then we will plug that into the calculator. We get a value of 14,700 newtons. So that's our normal force, and then we can take that and sub it into equation number 1. So anywhere we see n in equation number 1, we will put in 14,700. And that's going to be equal to 1,500 kilograms times AX, which is what we're trying to find. And so we can solve for this by dividing the whole equation by 1,500. And so we get a value for the acceleration here of 7.84 meters per second squared. So this is the final answer for our problem here.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we are asked to write a realistic problem for the equations that are given to us in the question. So I think it's fairly clear that these equations are force balance equations. One is for an x direction, one is for a y direction. And then we just need to make a problem that kind of fits those forces and those accelerations presented in the equations. So there's a number of different answers to this question. This is just the one that I came up with. So a 20 kilogram block is pulled up a 20-degree incline such that it has an acceleration of 2 meters per second squared. The coefficient of friction between the block and the plane is 0.2. What is the pulling force required? So I'm going to start off with the free body diagram, and then I'm going to write out the equations so that hopefully it becomes clear why I chose the problem the way I did. So free body diagram, we've got the inclined plane. It's got a 20-degree angle. We've got the force of gravity pulling straight down. We've got the normal force perpendicular to the surface, as always. And then we're going to have the friction force opposite the direction of motion, and the tension force or the applied force is directed up the plane. So the directions that we should use for this are y is perpendicular to the plane, and then x is down the plane. Actually, we'll make x up the plane. So why does this problem fit the equations? Let's go ahead and write out the equations and make sure that they match. So we're going to do F net x. So in the x direction, we've got a tension force. We've got a component of the gravitational force. We've got the friction force, which is going to be the coefficient times the normal force. I guess I use n because that's what they used. So let's change this here. Little n. Okay, and then I've also got a component of the gravity force. That's going to be mg sine 20. And the reason that it's sine, you can take a look at the components here. This angle here at the top is always going to be the same as the inclined plane. Okay, so we've got our first equation, and that actually matches the equation that's given in the problem if we go ahead and sub all the numbers in that we are given. So that the only two unknowns here are the normal force and that pulling force that we're asked to find. Okay, and then let's do the equation for the y direction. So that's going to come from F net y equals may. The acceleration is 0 because we're not accelerating down into the plane or away from the plane. So that's going to equal 0 here. And the two forces in the y direction are the normal force and then the y direction of the gravitational force. So that's mg cos 20. And so we can sub the numbers in. We get 29.8 cos 20. So now we have the two equations that were given in the problem. Our problem that we've written clearly matches these equations, and all we need to do is solve this for the tension force, which is the pulling force. So what I'm going to do is I'm going to pull everything to the right-hand side here on this green equation, and that will give me a normal force of 184 if you just throw all that into your calculator. And then I'm going to sub the normal force into this equation up here for tension. So anywhere I see normal force in that equation, I'm going to go ahead and sub it in. Okay, let's go ahead. We'll have a peek up here. What do we write? Minus 2, 9.8 sine 20. And that's all equal to 20 times 2. And so when we bring these two terms over to the right-hand side and we plug that all into our calculator, we get a tension force of 143 newtons. So that is the pulling force required to accelerate this object 2 meters per second up the ramp.
हम तक पैसे? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we are asked to write a realistic dynamics problem to fit the equations that are given and draw a free body diagram as well as finish the solution of the problem. So this problem presents three equations to us. The first two are force balance equations, and the second one is just our regular formula for the force of friction based on the normal force. So really, we're just looking at, another dynamics problem. If you have solved enough of these already, I think it's fairly intuitive to come up with a problem. Obviously, answers will vary here. So the one that I chose was a sled is pulled along a surface with a force of 100 newtons, directed 30 degrees above the horizontal. The coefficient of friction is 0.2, and the mass of the sled is 20 kilograms. What is the acceleration of the sled? So the reason that I chose this scenario is because in each of the x and y equations, there is the 100 newtons times cos 30 and then the 100 newtons times sine 30. So I knew that had to come into play somewhere. So I just made an applied force that had those parameters to it. So what is the free body diagram? So we've got that applied force we were just discussing, and that is at an angle of 30 degrees. We've got the normal force, as always, is going to be perpendicular to the surface. Gravitational force pointing straight down, and then the force of friction will be opposite the direction of motion. So that's our free body diagram. Let's go ahead and start to solve these equations. So I think the easiest one to start with is equation number 2, and we can just pull everything over to the other side and solve for n. So let's start with that. So that's going to be equal to negative 100 newtons sine 30 minus 20 kilograms times 9.8 meters per second squared. And sorry, this should be plus. And so when we put that into the calculator, we get a value of 146 newtons. What that allows us to do is take the third equation up here and just plug in the normal force into that equation. And so that will give us the friction force. So the friction force here is about 29 newtons. And then we can take the friction force and sub it into equation number 1. And that will allow us to solve for the acceleration. So we've got 100 newtons cos 30 minus the friction force is equal to max. Oh, sorry, what's m here? It's 20. And actually the ax is what we're trying to find, right? So this is good. So I'm just going to sub in friction here. So we've got 100 newtons cos 30. And I'm going to divide both sides of the equation by 20. So that gets rid of that. And so when you plug that all into your calculator, you should get a value for acceleration of about 2.9 meters per second squared. So that is one way that we can interpret the equations and solve them in this case.
हम तक पैसे? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So in this question, we're given a scenario in which we're told to hold our palm perpendicular to the ground, and it's pointed out that you can't hold anything in your palm this way because it would fall straight down. Then we're told that if you use your left hand to hold a small object there, such as a coin or a ball, against the palm, then you can quickly let go of the object and swing your hand towards the left across your body parallel to the ground, and the object won't slip and fall. So the first part of the question asks us, is the condition for keeping the object against the palm one of maintaining a certain minimum velocity or of a certain acceleration? So this is an interesting little question. So let's think about, first of all, if we just got an object against our palm, what's happening there in terms of a free body diagram. So let's assume this is our object. This will be the palm here. And we know that there's always going to be a force of gravity acting on such an object. And in order to get that object to stay, we would like there to be a force of friction acting in the upwards direction, balancing out that gravitational force. But we know the only way to get a force of friction is to have a normal force that is directed perpendicular off of the palm. So when you just try to place an object against the palm there, and not moving your hand, there's no normal force there to provide that friction force, and so that's why the object just falls straight down. But if we are moving our palm, and in particular, if we are accelerating our palm, then there has to be a force there providing that acceleration, and that is the normal force. So if palm is accelerating, there must be a force there to provide it, and the only force that could be is the normal force. If that acceleration is large enough and the normal force is large enough, then we will have a great enough static friction force to oppose gravity. Okay, so the condition here in order for the object not to fall is to have some minimum acceleration that provides a great enough normal force. So condition is a minimum amount of acceleration. And the reason that velocity doesn't really factor in here is even if you're moving it at your palm at a really high velocity, but there's no acceleration, then there's no, there doesn't need to be a net force in the left or right direction, and there doesn't need to be a normal force, and the object would fall off if the acceleration is 0, even if you're moving it at a high velocity. So this is the answer to part A. And then for part B, we have to do a little calculation. So we're told that we've got a So we're told that we have a mass of 50 grams. So that's going to be 0.05 kilograms. And we've got some coefficients of static friction and kinetic friction. And we'd like to determine the acceleration that we need in order to prevent the object from falling. Well, we know that we need a certain amount of static friction to keep the objects in place against gravity. So I think a good place to start is to calculate that static friction. So what static friction balances out gravity? Well, gravity is going to be equal to m times g. And so the static friction force that we need is 0.4905, the value of gravity on this object. Once we have the static friction force, we can then calculate the required normal force, right? So we know that, let's say, the static friction force is equal to mu s Fn. That's the value of the maximum static friction force. And this is the value that we do want to use because that will give us the minimum amount of normal force that would be needed. So let's see. We want to calculate normal force, so we're going to isolate this for normal force. So this is just Fs over mu s. And so we've got 0.4905 divided by 0.8, and that gives us a value of normal force of 0.613. So now we have the force in that direction. That's the only force that's acting on the object in that direction. And so we can simply calculate the acceleration using F net equals ma. This is in the x direction. The only force, as I said, is the normal force. So normal force is equal to max. So ax is equal to normal force over mass. And so we just take that 0.613 and divide by 0.05 for the mass, and we get a value of about 12.3 meters per second squared. So this is the minimum acceleration that is required in order to keep that object from falling. This is because the normal force is enough in this case that we have a high enough static friction force to, to resist the gravitational force that's trying to pull the object down.
हम तक पे sir? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we're told a machine has an 800-gram steel shuttle, and it is pulled along a steel rail by a cord. The shuttle is released when the elastic cord has 20 newtons of tension and the angle is 45 degrees. And the question asks us to calculate the acceleration. So this is kind of an interesting problem just because of the forces on the shuttle. So let's first look at a free body diagram. So we know that we're going to have that elastic force or that tension force from the cord, and that's going to be the 20 newtons directed at 45 degrees. And then we'll have a gravitational force pulling the object straight down, as always. And there will be a normal force between the shuttle and the rail, but we actually don't know which way it's going to point because we don't know which is more, the tension force in the y direction or the gravitational force. So depending on how big that tension force is, we're going to get either a normal force in the down direction or a normal force in the upwards direction. So let's just assume that it goes in the upwards direction. If we're wrong, then we're going to get a negative sign when we calculate normal force. And we'll know that we assumed the wrong direction. And then we can also put in our friction force, which will oppose the direction of motion. So in order to find the acceleration, we're going to need to use our regular force balance equations. Let's start with the x direction. So in the x direction, we have the x component of tension, subtract the friction force. And the x component of tension we can calculate using Ft cos 45 degrees. And that will be equal to and then the friction force will be equal to the coefficient of kinetic friction times the normal force, and that's going to be equal to max. The problem with this equation is, we're looking for ax, but we also don't know fn, so that's the second unknown here. So we can go ahead and analyze our y direction and see if that will give us the normal force. So let's do a force balance equation for the y direction. Of course, for the y direction, the acceleration is equal to 0. So the net force will be equal to 0 because the object's not moving up and down. It's just moving to the left or the right. So the net force in the y direction, that's going to be the y component of the tension plus the normal force minus the gravitational force. And so the normal force will be equal to gravity, mg, minus the y component of the tension force. So I'll just write that as Ft sine 45 degrees. So using this, we can absolutely find what that normal force is going to be. Using the mass is 800 grams. So instead of substituting in 800, I'm going to do 0.8 because it needs to be in kilograms. So 0.8 kilograms times g minus 20 sine 45. And when you plug that into the calculator, you should get a value of approximately negative 6.29 newtons. And so we did actually get a negative here, right? Because we assume that the normal force would be in the upwards direction. It's actually in the downwards direction because the tension force is overpowering the gravitational force. So in order to keep the object from being stationary in the y direction, the normal force actually has to be directed downwards here in this case, which is kind of cool. But when you go ahead and use the normal force in this equation here, for the x direction, you're just going to use the magnitude of the normal force because that's what the friction force depends on, just the magnitude. So we don't need to put a negative in there at all. Okay, so now that we have the normal force, we can go ahead and substitute everything into that equation that we made for the x direction. So we've got 20 newtons for tension. For the coefficient of friction, we've got steel on steel here, right? The steel shuttle is on the steel rail, and so we can use the coefficient of kinetic friction for steel on steel, so that's 0.6 if you look in the table. And the normal force is 6.29. Again, we're going to substitute mass as 0.8. And so on the left-hand side here, we're going to get 10.4. And so all we need to do to isolate the acceleration in the x direction there is divide by 0.8 on both sides. And so we get acceleration in the x direction, or the overall acceleration, has a magnitude of about 13 meters per second squared. So this is our final answer here.
हम तक पैसे? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we are shown an accelerometer. It's a device for measuring the acceleration of cars and planes. The ball is free to roll upon a parabolic track, which is described by y equals x squared. And there's a scale on the bottom that is used to measure the position x. What we need to do is find an expression that allows us to use a position x to compute the acceleration in the x direction. And then we need to do a little calculation in part B. So let's start with part A. And we're looking for the acceleration, right? So we definitely need to analyze the forces that are acting on this ball. And one thing to notice is that a curved track at any one point is kind of like an inclined plane, right? So we can draw a tangent to the curve. I'll use a different color for this. So we can draw a tangent, which is a line that's parallel to the curve and just kind of kisses the curve at that point. And the reason why this is interesting is because then we can kind of know what the direction of the normal force is, because the normal force will always be perpendicular to the surface. So in this case, it's going to be perpendicular to that tangent. So the forces on this ball will be a normal force in this direction, as well as our regular gravitational force directed straight down. The difference between this situation and an inclined plane is that the acceleration is not directed along that tangent, it's directed to the right. It needs to have, when it's in equilibrium, when it comes to that resting position, it needs to have the acceleration of the train or the car, the airplane, whatever it is, to the right. Okay, so the net acceleration here is going to be to the right. And that's the same acceleration of whatever vehicle this accelerometer is placed in. So this will kind of inform our net force equations a little bit, and kind of change things from what the normal situation is on an inclined plane, if that makes sense. So let's think about how we're going to get to the acceleration in the x direction. The only force acting in the x direction is the normal force, and that's a component of the normal force. And the question is, how do we know what the the normal force is, right? Well, one thing that we can notice is that the acceleration in the y direction has to be 0, right? It's not moving up or down. It's not accelerating up or down. It's only accelerating in the x direction. And so if we look at the forces in the y direction, that's the gravitational force and the normal force in the y direction. So we know that these two things have to be equal to one another. So the gravitational force is equal to Fn cos theta. Now, what angle am I referring to here? I'm referring to this angle in the triangle that we can make with the tangent. And how does that relate to the normal force? Well, we can draw some components in here for the normal force. And since all of these lines are perpendicular to one another, sorry, not perpendicular to one another, but let me show you how to find what the angle is, where that angle theta is in the Fn triangle. So we can make our normal kind of triangle with FG. And we know that this angle between that kind of perpendicular to the plane direction and FG is also theta, right? And so this line perpendicular to the plane and the horizontal and the vertical have that angle theta between them. We know that angle in the FG triangle is the same as the angle in this FN triangle. And so we can see that FN cos theta is equal to FG, right? The vertical component of FN is equal to FG. So that's the first thing. And then we want to get at what Fnx is. So we should do another little formula. We know Fnx is Fnx over Fn should be equal to sine theta. And so we can isolate for Fnx. That will be equal to Fn sine theta. And we can then take the first equation, rearrange it for Fn. So that's going to be Fn is equal to Fg over cos theta, and plug that into this formula for Fnx. So that gives us Fg over cos theta times sine theta. But sine theta divided by cos theta is just tan theta. So we can simplify this to Fg tan theta. That's the x component of the normal force. Now, we want an expression for the acceleration, not in terms of theta, but in terms of x. So how can we relate this theta here to x? So one thing that I'll point out is that the sides of the triangle represent changes in y and changes in x. So one side of the triangle here will represent dy and the other will represent dx. So when you look at tan theta is equal to dy over dx. Okay, another way to look at this is, okay, we know that the slope of this line, the tangent, should be equal to the derivative of the function. So, and since the slope is equal to rise over run, then tan theta is going to be equal to the slope. And so what is the derivative of y with respect to x? Well, y is x squared, so we just get 2x here. Okay, so now we know that the normal force in the x direction is Fg 2x, and we can go one step further and get the acceleration because Fnx is our net force in the x direction. So Fnx will just be equal to max. Fg is mg. And so we can get the acceleration is equal to 2x times g. So whatever the x value is, we just plug that in and we can get the acceleration. So that's what we are asked to do in part B. We're given an x value. The x value is 20 centimeters. So that's 0.2 meters. And so the acceleration is equal to 0.4 times g. And 0.4 times g is about 3.9 meters per second squared. So this is your final answer for part B, and this is the final expression for part A up here.
हम तक पे sir? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So here in this question, firstly, to find the object's acceleration between 0 to 4 seconds, we need to calculate the slope of the velocity time over that interval. So acceleration is calculated as change in velocity upon change in time. So from the graph, we can see that object's velocity increases from 0 meter per second from 0 meter per second to 20 meter per second over the interval of 0 to 4 seconds. Over 0 to 4 seconds. So the change in velocity comes out to be 20 meter per second minus 0 meter per second, and that is equals to 20 meter per second. So, and here the change in time is 4 second minus 0 second, and that is equals to 4 seconds. Now, the object acceleration comes out to be delta v upon delta t, and that is equals to 20 meter per second upon 4 seconds, and that is equals to 5 meter per second square. Now, to find the object's acceleration between 4 second to 9 second, acceleration between 4 second to 9 second, we again need to calculate the change in velocity upon the change in time. Now, from the graph, we can see that velocity decreases from 20 meter per second, velocity from 20 meter per second to minus 10 meter per second over interval of 4 second to 9 second. So the change in velocity comes out to be minus 10 meter per second minus 20 meter per second, and that is minus 30 meter per second. And the change in time is from 9 seconds to 4 seconds, and that is equals to 5 seconds. Therefore, the object's acceleration is equals to minus 30 meter per second upon 5 seconds, and that is equals to minus 6 meter per second square. So I hope this answered your question. Thank you.
हम तक पे sir? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we're told an object is moving through a liquid. It has a drag force equal to BV. And we are also given an expression for B based on the viscosity of the liquid. We need to find an algebraic expression for Vx as a function of time. And then we are also asked to find how long it will take for horizontal speed to decrease to 50% based on this expression that we find for part A. So let's go ahead and tackle part A. This will take a little bit of calculus, so if this isn't something that you're super comfortable with, then this will definitely be more of a challenging question. Let's start off with the physics though. So the only force that's going to be acting on this object is the drag force. So we know that the drag force is going to be equal to m times a. And the drag force will be in the negative direction relative to the object's motion, right? Because it's a motion that is opposing, or it's a force that's opposing the motion. So we know that the drag force will be equal to negative BV. And so we can create a little formula here that relates V and A. And this is where the calculus is coming in. So what I'm going to do is I'm going to solve this for A. And what we're going to do is we're just going to define a constant C. So C will be equal to B over M. And I'm going to take this equation and I'm going to use the fact that acceleration is equal to the derivative of velocity and sub that in. So now I've got an equation that says the derivative of the velocity is equal to negative CV. And I can rearrange this to take all of the V's over to one side. That's going to give me dV over V will equal negative C dt. And then we want to integrate this formula to get an expression for V in terms of time. So we're going to integrate from the initial state to some other final state. So in this case, we will integrate from 0 to some time t, and we're going to use v0 as our initial velocity. And the derivative of 1 over v is ln v. So we get ln v minus ln v naught is equal to minus t minus c, t minus 0, so just ct. And we can consolidate ln v minus ln v naught with rules for logarithms. And then we can get rid of the ln by taking or raising both sides to, or taking both sides and raising e to them. So e to the power ln v over v naught, e to the power minus ct, and e to the power ln, that cancels out, and we get v over v naught is equal to e negative ct, and v is equal to v naught e negative ct. Now remember, c is b over m, and we can also substitute in for b here based on what we were given in the question. So with all of the constants written in, we get a final formula that looks something like this. So this is our answer to part A here. We've got an expression. Now in part B, we need to calculate how long it's going to take for the velocity to reach 1/2 of the initial velocity. So what I'm going to do is I'm going to take this formula that we just derived and substitute in 1/2 v naught on the left-hand side. And I'm going to go back to using that constant here for a second, just so I don't have to write that all out. So v naught and v naught cancel. And I want to solve for time here, so I'm going to take the logarithm of both sides. So ln 1/2 ln e to the minus ct. And ln and e, again, they cancel each other out. So we've got ln 1/2. That's equal to negative 0.693 approximately, and that's going to equal negative ct. Let's go ahead and cancel the negative, so we'll just make it positive on both sides. And let's calculate what C would be for this particular scenario that we were given. So let's do a little equation on the side here. So C is 6 pi n r over m. And the n we were given was 1 times 10 to the minus 3. The r is 4 centimeters. So 4 centimeters is the diameter, 2 centimeters is the radius, so 0.02 meters, all over the mass, which is 0.033. And so when we put that all into the calculator, we get a value for C here of 0.0114. And you don't have to do this separately, but I just think it's a little bit easier. So let's sub that in here. So we've got 0.693 is equal to 0.0114 times t. So t is just 0.693 divided by 0.0114. And so when we put that into the calculator, we can get a value of 61 seconds. So after approximately 61 seconds, the speed will have decreased to approximately 50% of its initial value if the only thing acting on it is this drag force that we have here. So yeah, that's the answer to this question.